Now let's try and find this new number I. Let's try and find where it is geometrically. So I stands for this number square root of -1, and it has the property when you square it, it becomes -1. So maybe you can start with the naive idea that this number I just so happens to be hidden somewhere on the usual number line. But you quickly realize that this is definitely not true, because I is definitely not a positive number, because positive number squared has to give us a positive number, and I clearly doesn't have that property. And I is not a negative number either, because if you square a negative number, we also get a positive number as well. So I is definitely not a positive number, it's not a negative number either, and it's obviously not the number 0. So you can see that I is definitely not on the real number line that we are used to. So what this means is that if you're trying to find I, we need to look elsewhere. We need to look beyond the regular number line. And so we need more than just the one-dimensional number line. We need to go beyond this one-dimensional system to find I. Okay, so to make further progress, we're going to look at this rather simple equation. So 1 times -1 is just -1. But because I squared is -1, what we can do is replace this bit here with 2 lots of I multiplying by itself. I squared is equal to -1. So these 2 bits are actually completely equivalent. Now what we want to do is try to think of this multiplication with -1. We're going to try to think of it as some sort of transformation that's such that when we apply it to 1, the transformation will take us to -1. So the act of multiplying by -1 is some sort of transformation that takes us from here all the way to here. And whatever that transformation may be, what we're going to do is take that transformation and then break it down into 2 smaller equivalent transformations, such that these 2 bits together will make this thing. And so once we have that, we will have a transformation that will represent what multiplying by I will mean. So, but the problem is, like, there could potentially be lots of different transformations that can take us from here to here, and we don't know which one. But keeping in mind the previous fact that we established, and that is I is nowhere on the number line, nowhere on the real number line. So to find I, we need to step off this one-dimensional system here. So with this fact in mind, the correct candidate for this transformation, you should realize, is that it should be a rotation by 180 degrees. So something like this. And with this realization, we can realize that multiplied by I, so how do we break this transformation into 2 smaller equivalent transformations, such that when we add it, we get the net effect of rotating by 180 degrees? Well, the answer to that is each of these things should be a rotation by 90 degrees. So we come to a very, very important realization for complex numbers, and that is we can visualize the act of multiplying by this new number I as the transformation of rotating by 90 degrees. Okay, with this really important realization, we can actually find the location of the number I itself now, because what this simple equation says is the following. We can start at the number 1 and then multiply by I. In terms of algebra, obviously that's equal to I. But in terms of the new geometry that we established, this bit here is telling us to rotate by 90 degrees. So what this is saying is that we can start with 1, rotate by 90 degrees, and that will take us to the new number I, take us to its location. So the diagram looks like this. And the new number I is right here. So now let's build something called the Argand diagram. So here we have the regular number line, and the numbers on the number line really tells us how many ones we want. So here we want 1 lot of ones, 2 lots of ones, 3 lots of ones, and so on. So we just discovered this new number I here, which is located here. And you can see that looking at this diagram, it's very natural to try and extend this axis in the same way that the real number line is fully extended. And the regular number line tells us how many regular ones we want. So if we try to extend this axis here, really the axis is trying to tell us how many i's we want. So here we want 1 lots of I, and then this should be 2 lots of I, 3 lots of I, and so on. So now we are ready to interpret numbers written like this, 3 plus 2i. So the 3 really tells us we want 3 lots of the regular numbers, so we're sitting here somewhere. And then 2i tells us we want 2 lots of I, so we're here. So you can see that this number really should be this point here, the intersection between these two ideas. So the number 3 plus 2i is this location here. So now let's give proper terminologies to everything we just learned. So we had the number line here, but with this new axis fixed to it, together we now have this new number plane. And this new number plane is referred to as the Argand diagram. And this number plane has 2 axes, the real axis, the regular number line, and also the imaginary axis, which tells us how many i's we want. And complex numbers, these new types of numbers, are nothing more than just locations and just points within this number plane. So here we got a complex number 3 plus 2i. And a complex number has a real component, a real part, which tells us how many real numbers we want. In this case, it's just 3. And a complex number also has an imaginary part, which tells us how many i's we want. And in this case, it's 2. And it's really important to make note of the fact that these real and imaginary components are just regular numbers. Okay, so if we want to specify a general complex number, we typically use the letter Z. And then to specify its real and imaginary components, we use the letters X and Y. And this way of writing complex numbers is referred to as its Cartesian form. And this is too long to write. We're sick and tired of writing all the words out, the real part and imaginary part. So we have a shorthand notation for these things as well. So they look like this. The real part of the complex number Z is X. And similarly, the imaginary part of a complex number Z is Y. And again, it's really important to realize that the real and imaginary parts, in this case X and Y, these things are just regular numbers. And if we wanted to label a different complex number, we typically use the letter W and then U's and V's for its components. So suppose we got 2 complex numbers Z and W. Well, we say they are equal only when their real components are the same and their imaginary components are the same. So in a diagram, if the real and imaginary components are the same, then that means that they must be the exact same location within our number plane. So if 2 complex numbers are equal, then they're the exact same point within this number plane. Next, let's talk about the really important notion of conjugates. So suppose we got this complex number here, 2 plus 3i. Its conjugate is also a complex number, but it's the complex number that's the reflection of this one along the real axis. So the complex conjugate of this thing is going to be 2 minus 3i. And you can see that this is true because when you take this reflection along this line, the real component is going to stay the same. And the imaginary component is going to have the same magnitude but opposite in sign. Let's look at another example. So suppose we got this complex number. Well, where is its conjugate? First of all, its conjugate is going to be the reflection of this along this red line. It's going to be located here. And in terms of its Cartesian form, we're going to have the exact same real component, but the imaginary component is going to be the sign changed. So it's going to be plus 2 now. And in the special case of real numbers, what happens when you take conjugates of them? Well, if you take the conjugate of the regular number 5, we're reflecting it along this red line here. But you can see that because of the position of the real number 5 here, when you take the reflection, nothing's going to happen. It's going to stay in the same spot. So when you take a conjugate of a real number, nothing's going to happen to it. But in general, when you got a complex number Z, located some random position here. When you take the conjugate, it's going to be the reflection. And if you've written your complex number with the letter Z, we're going to denote its conjugate with a bar on top, so Z bar. So the conjugate of this is going to be A minus IB. And conjugates are really important because the complex number and with its complex conjugate share a lot of very important properties together. Okay, let's do a summary. So we got this complex number I that stands for the square root of -1, such that its square gives us -1. And we realized through transformations that multiplying by I actually means to rotate by 90 degrees. And with that fact, we're able to deduce the location of I itself. And then having this location made us realize that we should build something called the Argand diagram, this new number plane here. And the number plane has a real axis and an imaginary axis. And within this number plane, we have complex numbers, which are nothing more than just points within this number plane. And we can write complex numbers as z equals to x plus iy, and this notation is referred to as the Cartesian form of the complex number. And a complex number has a real and imaginary component, each written like so. In this case, the real component is x, and the imaginary component is y. And it's really important to remember that x and y just stands for regular numbers. Okay, we also looked into the notion of conjugates. So given a complex number, we also have its conjugate, which is the reflection of the complex number along the real axis here.